Yeah. Okay. Hello again. I am gonna talk about the impossibility results that I hinted a little bit in my previous talk today about the PCD security, and in particular, I'm gonna talk about what is relativized succinct argument in a random oracle model and why they don't exist. This is recent joint work with Annalisa and Alec. So I'll start with defining snarks as a review. First, a brief recap on what is random oracle model. Random oracle is actually a set of distribution indexed by natural numbers. So each OL here is a uniform distribution over all functions of output length L. And then in the random oracle model, a snark behaves roughly the same as in the standard model. The prover and the verifier want to decide whether the instance X is in the language. The prover sends a short proof string to the verifier, and then the verifier decides whether to accept or reject. We have our usual security notion, completeness and soundness, where completeness is saying that if the instance L is in the language, then the probability that the verifier accepts is 1. So the verifier always accepts when the prover is honest and when the instance is in the language. And also soundness, which is saying that for all bounded, both query bounded and time bounded adversary, the probability that if X is not in the language, but the prover successfully convinces the verifier, this probability is very small, upper bounded by this small parameter lambda, epsilon. And so that was a brief recap on snarks in the random oracle or in oracle models in general. But what we are going to focus on today is actually relativized argument or relativized snarks in the ROM. So relativized here just means that now we're going to deal with languages that are relativized, meaning that the language now is indexed or is related to the oracle function f that we have. A very simple example is that we can, a simple oracle or relativized language LF is a set of xy such that y is equal to f of x. So the membership of x and y in this language LF depends on the oracle function f, which is relativized. And relativized argument, therefore, is almost the same as normal argument, just that now they're dealing with this relativized language that depends on the oracle function f. So the completeness and soundness are defined similarly, except that they're working for a relativized language. Okay, so that was the definition, but why do we care about relativized argument? Why do we study them? The first motivation is that they're very useful in constructing verifiable distributed computation. And let's look at this scenario where we have 3 distributed parties, Alice, Bob, and Carol. And now Alice sent Bob a proof pi a for some statement phi a. And then Bob wants to send another proof to Carol that not only testify the statement phi b, but also show that Alice actually already sent a proof to Bob. So this is the proof of proof concept that we actually heard about earlier this morning. This is a very simple abstraction of what's going on in incrementally verifiable computation and proof carrying data. So how does Bob produce this proof of proof pi b? The answer is that he used relativized argument for the relativized language C set, which contains the set of circuits and input such that there exists a witness where the circuit given oracle access to the random oracle, the input x and the witness w, a value is to 1. So this is normal, our favorite NP-complete relation C set, but relativized to the random oracle. And then Bob actually have implicitly constructed an oracle recursive circuit, and then the circuit first check whether the statement phi b is correct, and then it check whether the verifier, the snark verifier for the circuit, accepts Alice's statement and proof. And then recursively, if Bob just outputs whatever proof that the relativized snark prover output, this phi b serves the purpose. It not only shows the correctness of the statement phi b, but also is a proof of proof for Alice's statement. Okay, and on the other hand, relativized argument can be very useful to handle efficiency issue that we see a lot in crypto, which involves recurring cryptographic computations, such as correctness proof for encryption, decryption, signature verification, and hash function. For example, let's consider a very common language that shows up a lot, depends on hash function. This language is an NP language that contains tuples n and y, such that n, y is in the language if there exists a witness x, such that if you repeatedly hash x for n times, you get y. So this is just a hash chain language that is in NP. And intuitively, Snark's construction for this hash language is going to be very expensive because the size of the snark would depend on the circuit that actually repeatedly apply h, the hash function, for n times, which has size at least n times the size of the hash function h. And does this mean that now it's necessary for us to construct very small size hash function, or in general to optimize the size of those recurring cryptographic computations? Fortunately, there is a potential alternative route we can take, again using relativized argument. In particular, we can treat the hash function as an oracle, and then relativized argument for this language do not depend on the size of the hash function anymore. And more specifically, if we know that for any NP language relativized to this hash function, we have a succinct argument relativized to this hash function, then those relativized snarks, they in particular do not depend on the size of the hash function because they have oracle access. So in general, relativization removes the need to optimize this recurring subcomputations. So a natural question to ask is that, yes, relativized arguments, they are very nice, but they seem super strong. Do they actually exist in any oracle models? The answer is yes. So we do have a bunch of constructions of relativized snarks in different oracle models, and in particular in the signed random oracle model, which combine random oracle with the signature scheme almost 15 years ago. And more recently, CCS22 constructed a relativized argument for all NP computations in the low-degree random oracle model, which is the low-degree extension of the normal random oracle model, and also more recently in arithmetized random oracle model. But all those oracle models, they are very hard to instantiate. We still have our favorite oracle model, the random oracle model, that is much easier to instantiate. And we ask, do we have relativized snarks in random oracle model? The popular belief is actually no, because CL20, a paper 5 years ago by Ziyi and Ale, they show that relativized probabilistic proofs do not exist in the pure random oracle model. And because most interesting snarks construction we know of, they're based on probabilistic proofs, then naturally people think this is a very strong evidence to show towards the fact that relativized snarks do not exist. But this intuition is actually wrong, because in the same paper, they show that relativized probabilistic proofs do not exist in the low-degree random oracle model. But as mentioned just here, we know that relativized snarks exist. So this is actually more involved than we expected. And in this paper, we give the first result formalizing the popular intuition that relativized snarks do not exist in the random oracle model. And in particular, we handle both deterministic computation and non-deterministic computation. And in particular, we know that trivially, relativized snarks exist for deterministic computation with t steps, where the verifier query complexity to the random oracle is t, because the verifier can actually afford to compute the problem itself. So this is a trivial baseline for deterministic computation, and we show a tight result. Namely, if we decrease just a little bit the verifier query complexity, relativized snarks do not exist anymore. If we kind of tighten VQ equal to t to little of t, it doesn't exist anymore. And similarly for n time, we know that trivially for a non-deterministic computation with witness size t, an argument, relativized argument, where you allow the proof size to be t, trivially exists because the prover can just send the entire witness. And similarly, we show a tight lower bound saying that if you just decrease the argument size a little bit from t to little of t, it doesn't exist anymore. And a very cute corollary of our result is that relativized IVC PCD does not exist in the random oracle model. And this is actually a open question. It has been an open question for a long time, but whether plain IVC PCD exists in the random oracle still remains open. We don't know how to show it using methods we have in this paper. And I also want to emphasize that our lower bound result, theorem 1, theorem 2, although like in this talk I focus on non-interactive arguments, they actually also work for interactive arguments. And also more interestingly, in the random oracle model, usually people care about lower bounds for pure query-bounded adversaries. In some sense, those adversaries are statistical. But in our work, we actually also rule out relativized snarks for both query-bounded and time-bounded adversaries, which imply that in this case, even if you assume both random oracle and also cryptography, you still cannot construct relativized arguments. Okay, so I want to spend a few minutes to briefly give the proof outline for the separation between non-deterministic computation and relativized argument. So in particular, the proof starts with choosing one hard language in n time t. So the lemma we're going to show is that there exists some hard language LO, such that LO is in n time t, but it does not have relativized argument that can decide it. And this LO is mentioned before. It is a set of languages. Each of them depend on the oracle function that you choose. And in particular, our language is a set of strings, all 0 strings of certain length, and such that there exists a witness W of length t, such that for every I in t, if you query the random oracle on W concat I, the first bit of the answer you get is 0. So this is very, very complicated. Let's look at an example. So I have two random oracle functions, the red one and the blue one. And let's say for simplicity, I only t is equal to 5. I only care about these 5 query locations. Witness concat 1, concat 2, so on and so forth. And if the answer I get, they always start with 0, the first bit of the answer is always 0, then X is in the language. Otherwise, if any of them start with 1, X is not in the language. So I claim that this language is a hard language. First, because you need T queries to be sure whether the instance X is in the language or not. And especially if you flip even one bit of F, you could change the membership of X. So for example, here, from the red F, you start with answers that looks like this. Clearly, X is not in the language because you have a 1 here. But if you just flip this one, you get a blue F prime where X is actually inside LF F prime. So in some sense, this LF is maximally hard in n time t. And now I want to show that relativized snarks do not exist for this particular language, LF, which I put it here for reference. So the proof starts with fixing some n such that x is equal to a all zero string of length n. And then I consider a particular random oracle f star such that x is not a member of LF star, meaning that some of the queries we care about give you answer where the first bit is 1. And now, for every possible witness, w in 0, 1 to the t, those are like all possible witnesses that we can consider. We define another function, fw, to be the same as f star, except that at those query locations that we care about, w concat I, we set the first answer to always be 1. So for example, if we start with f star that looks like this, we have like 1, 0, 1, 0, 1. It's clear that x is not in LF star, but if I set all the first bits into 0, we know that trivially x now is a member of LFW, just by the definition of FW. And also, since O is like a distribution over all possible functions, and clearly FW here is also a function, then FW is part of the random oracle as well. So it's another oracle function. So everything is well defined. And now I have a very, it's our key technical claim saying that for every oracle function that we can take, there exists a very large set, which is a subset of all my witness set, such that for every witness in this large set, the verifier doesn't make meaningful queries with high probability. Because this w concat I are all the queries that matter, that we care about. And now I claim that there is a big set such that verifier just don't make meaningful queries. And the intuition for this claim is that without a very big argument proof string, the verifier don't know what queries to make. It cannot make meaningful queries. And then by the soundness of the argument plus the fact that x is not in LF star, we know that the probability that the verifier accepts given oracle access to F star is small for efficiently generated proof string. And by point 4, this main technical claim, we know that for every W in this big query set QF star, the probability that the verifier accepts when given oracle access to FW is roughly the same as the probability that the verifier accepts when given oracle access to F star. Because inside this special query set, the verifier doesn't make any meaningful queries. So it cannot distinguish FW from F star. And from 5 and 6, we know that this probability where the verifier given the oracle access to FW accepts is very small because of soundness. But this is a contradiction to the completeness because we know that X is actually part of the language. So that's the overview of the proof. I'm going to skip the technical overview for this key claim, but you can check it out in our paper or ask me afterwards. So I want to spend the last few minutes to discuss a few open problems that we raised in the paper and also inspired by talks yesterday. So the first one is about the low-degree random oracle model. And as I mentioned before, low-degree random oracle model is actually the low-degree extension of the normal random oracle model. where each PL is the uniform distribution over all polynomials of low degree, polynomials of n variables and individual degree MOSD. So the first open problem we raise is whether one can rule out relativized snarks in the low degree random oracle model, but secure against only query-bounded adversaries, contrary to what we proved for random oracle model. And the reason is that in this CCS 22 paper, they actually constructed relativized snark for both query-bounded and time-bounded adversaries. So this is the best we can hope for an impossibility result. And then there are two natural routes we can take to try to attack this problem. The first one is, what if we just try to generalize our proof in the random oracle model? But this doesn't work because the flipping or the setting of FW, the new random oracle function we look at to contradict soundness and completeness, relies on this setting or like reprogramming of the random oracle. But in general, you cannot do it for low degree random oracle because there's no guarantee that once you do the flipping, FW still is a low degree polynomial. So this doesn't work. But how about taking the impossibility from relativized probabilistic proofs? Why? Because CL20 showed that no relativized probabilistic proofs exist in low degree random oracle model, and since probabilistic proofs are a very common subroutine to construct snarks, maybe impossibility there give us some intuition about impossibility here. But there is a caveat in this approach as well, because CL20 only showed the impossibility for a specific f in a specific low degree random oracle function, or actually more accurately, a group of f with non-zero measure. But since we're dealing with snarks, where the security notion are average case, we actually need a more uniform notion of separation, where we need the impossibility to hold for a uniformly sampled oracle function. So the very intriguing question is whether they actually exist or not, and now it's not super clear. And the second question we raised is about characterization results on oracle models. So let's look at a kind of roadmap of all the oracle models we discussed in this talk. So we start with some like very structured protocol that's very easy to learn or predict. And then we know that it's very easy to construct relativized snarks because we can just learn the oracle and use the non-relativized snarks. But we also have low degree random oracle model, which is like in the middle, not super easy nor super hard to learn or predict. In this case, we know that we can construct relativized snarks with crypto, but the conjecture is that without crypto in the pure LD ROM, we cannot construct it anymore. And lastly is the random oracle, which we show that there is just no relativized snarks with or without crypto. So then the question is, with this vertical line, where should we draw a horizontal line to, in which like below the horizontal line, relativized snarks exist, and above it, relativized snarks exist, and or more formally, whether one can give a sufficient and necessary condition for an oracle that separates deterministic or non-deterministic computation with existence of relativized snarks. And lastly, some insights into Fiat-Shamir transformation that's related to the talks yesterday. So we know that in the standard model, if we take an interactive protocol, we can do Fiat-Shamir interaction to get a non-interactive protocol in the random oracle model. And then we do heuristic instantiation of this random oracle non-interactive protocol to get a non-interactive protocol in the standard model. But this is problematic because sometimes this heuristic instantiation step is insecure. And in particular, there is this line of diagonalization attacks works that show that in some cases this is insecure. And then yesterday, Elon told us that if you start with a relativized interactive protocol in the random oracle model, and you do their extended Fiat-Shamir transformation, you end up with a relativized non-interactive protocol in the random oracle model. And this has proven security in the random oracle model, and more significantly, a big class of this white box attacks actually relativize, meaning that if you take the normal Fiat-Shamir and you plug in the relativized version of the protocols that they care about, this Fiat-Shamir resulting non-interactive relativized protocol end up being insecure in the random oracle model. Therefore, this extended XFS is secure against many existing attacks because of this relativization barrier. And then another kind of vague but cute question we want to ask is whether Fiat-Shamir transformation is secure in other random oracle models, especially the ones that we look at where they actually have constructions of relativized arguments, like the low-degree random oracle model and the arithmetized random oracle model. So that's everything I want to talk about. Thank you.
Thanks, Ziyi.
Hi, thanks for the interesting talk. Maybe I just missed, but I wonder where you use the succinctness condition in your impossibility proof.
Okay, so this was the part, the technical claim that I mentioned, the one that's pink. So here, to prove this claim, we use succinctness. And in particular, we want to argue, or we argued that if the argument string is short, which is the definition of succinctness, then the argument verifier do not know where to query. And in particular, for a large set of possible witness, it cannot make any meaningful queries.
So it means that there is a possibility that so you can get the relativized NISCs. You just showed that the relativized snarks are not possible.
Yes.
So is there a possibility that you
without succinctness,
yeah,
they
right.
are very possible. So in the results that, sorry, this is going to take. So here, for example, trivially, if you allow the proof string to have length t, then this trivially exists because the prover can just send the witness. And also in a talk I gave this morning, security bounds for proof carrying data, we actually give a construction of relativized non-succinct argument in the random oracle model. So that's slightly non-trivial, and it can be used to construct PCD or IVC.
Yeah, but I think he's asking about what if you want to add zero knowledge to this? So kind of you cannot do the trivial construction.
Okay, if
right?
you
don't
add
care
zero
about
knowledge,
succinctness, but you want zero knowledge.
That's a great question. I actually don't know if you would be able to prove the same impossibility if you remove succinctness but add zero knowledge. But I'm guessing probably. I'm not sure. This is actually an interesting question to
Very
think
good
about.
question. Yeah.
Yeah.
Any other questions? I wanted to say it would be like kind of interesting saying, okay, you had this slide where we don't have relativized snarks in the random oracle model, and then we have this other models, right? And it's not clear where to draw the line.
Yeah, it's gonna take a while.
It's okay, we have time.
Yes.
Yeah. Yeah, I found this very interesting, like saying, okay, I'm gonna have a possibility result for some family of functions in the sky, not random oracle, not low degree, and then like, okay, what is the minimal properties that I need from this family for the impossibility result to kick in? and then kind of have one proof that captures, you know, all the impossibilities and really like draws this line in a sharp manner.
Yeah.
Yeah.
This open question has been puzzling me for at least the last 2 years. So I really think it's a cute question. So if anyone solve it like now, let me know.
So what crypto did they need for the positive result?
That
The
one,
CCS, right? So it's,
CRH.
CRH.
Yeah.
Okay, so it's a CRH separate from the Oracle. Yeah. Okay.
Yeah. So they need both the Oracle and CRH, and they do some fair smear on the accumulation scheme inside.
Okay, let's thank Ziyi again. And yeah.